Alright, for this problem we have to realize that this is a two-step problem. So let's first start by listing out our variables. The first thing that we notice is that we have a wavelength, which is lambda, of 1 times 10 to the minus 9 meters. And they're asking you to find the energy of one photon of this radiation. Energy is E, and I don't know that, and that's in joules. So what's my formula for energy? Energy is equal to Planck's constant times frequency. So what's Planck's constant? Well, it's a constant, so it's the same number every time, which happens to be 6.626 times 10 to the negative 34 joule seconds. But I don't know the frequency. So how am I going to find the frequency? Well, I know that if I have the wavelength, I can use speed of light is wavelength times frequency to find the frequency. And what is the speed of light? Well, that is 2.998 times 10 to the 8th meters per second. So what I'm going to do is I'm going to find frequency by getting rid of wavelength, bringing it over to the other side. And when I do that, I'm going to plug in speed of light and wavelength. So 2.998 times 10 to the 8th meters over seconds divided by the wavelength, which is 1 times 10 to the minus 9 meters. And the meters cancel out. That gives you your frequency. Now when I do that, I use my calculator. Remember to use your EE button, and you're going to get 2.998 times 10 to the 17th per seconds, or hertz. That's frequency. And now we can take that number and plug it in up there in our original formula. So when I do that, I'm going to do it down low so we can all see it. Energy is equal to Planck's constant, 6.626 times 10 to the minus 34. And then I'm going to multiply that by 2.998 times 10 to the 17th per seconds. And again, use your EE button, and you end up with 1.99 times 10 to the minus 16th joules, which isn't a whole lot of energy. And that's how you do that problem.